In September of 2021, China finished building its first test thorium-fueled nuclear reactor. What exactly is this technology? And why is an event like this crucial for the development of nuclear power? So thorium was introduced as a potential energy source in the dawn of the nuclear age, with the first test reactors being developed shortly after, from efficient green power to thorium-powered planes. Except, it never happened. So why did this not occur? If it really has these large benefits, then why has the technology not been realized? My name is Joaquin Revello, and today we're going to be looking at the engineering, the economics and management, as well as the sustainability of thorium-powered nuclear reactors as a source of sustainable energy. It could spark your innovation to help create technology that could save the world. So the design of the thorium nuclear reactor is quite different from the standard light water U-235 that you are probably aware of. If you do not know the engineering behind the classic light water reactors, I would strongly suggest you reading some articles on the topic before. I've added one in the description down below. However, what's most interesting and unknown about the classic reactor technology is that approximately 96% of the uranium in the rods goes unused. And these unused portions of the rods actually require a reprocessing plant to convert this back into usable fuel. Because with solid uranium-235, there is a buildup of noble gases inside of the fuel rods, which prevent the chain reaction from really flourishing. On top of this, the solid pieces of uranium start to get damaged over time, which is due simply to the radiation that leads to cracks inside of the fuel rods, or more specifically, the solid lattice of the rods, which again is another obstacle to making the chain reaction progress and thus must be sent to a reprocessing plant to create new fuel rods. So a disruption in the water cooling supply could very well lead to a catastrophic failure as the rods are unable to be cooled. So the solution to modern day reactors? The thorium reactor, which consists of, well, you guessed it, thorium atoms as fuel. So why thorium atoms? First, thorium-232 is not a fissile-able material, which means that if the thorium does split somehow, it is not the splitting of the thorium atom that creates that release in energy. Rather, when it does absorb a neutron, it turns it to protactinium-233, and then into uranium-233. So it's the U-233 that releases the energy. And it's the 233 isotope that is actually more fissible than the 235, with the probability of fission of the 233 being approximately 91.2% compared to its absorption. Hence, it's not the thorium atom splitting that releases the energy, but rather its product, U-233. This releases on average about 2.5 thermal neutrons, which means that about half the time the reaction produces 2 neutrons or 3 thermal neutrons. These thermal neutrons are extremely desirable because they have a large chance of continuing the chain reaction, from approximately 20,000 to 2.2 kilometers per second. If you haven't realized already, the production of these thermal neutrons is already a massive positive. The technical term here is that of thermal breeder reactors. Essentially, this means that no additional U-235 is needed for reactivity boosts, unlike in fast reactors with the use of graphite as the moderator. Additionally, compared to the light water reactors, these thorium salt reactors, which the design will soon see, can add fuel without having to stop the reaction, leading to power generation without stopping. However, what's really great about thorium is its abundance, which is approximately 4 times more abundant than uranium on Earth's crust. We'll take a deeper dive at this in the economics and management section of the video. And before I do continue with the engineering of the molten salt reactors, I would just like to take a second to state that this video takes dozens upon dozens of hours to make. And as of right now, I don't have any sponsors, so I would appreciate all the support you would give me, as I am studying in a very rigorous program here at the University of Pennsylvania, a dual degree between the engineering school and Wharton, known as Management and Technology. And because of that, there's a lot of stuff to do, so I would appreciate any support that you would give me, such as sharing it with a friend. Anyways, back to the show. So what exactly is the reactor design? The reactor design with the most potential is the liquid fluorine-thorium reactor, also known as LFTR. Here, the thorium is bonded with fluorine and dissolved into a liquid salt. of which it is much safer and easier to control liquid than superheated water. This reactor is then heated to 700 degrees Celsius, which is approximately 400 degrees hotter than a standard nuclear reactor and 663 degrees hotter than a standard grizzly bear. This large temperature is allowed as water is not used as a moderator. In fact, for water to stay a liquid inside of the 300-degree uranium standard reactors, the pressure of the pipes must be around 14 megapascals, which is roughly 150 times atmospheric pressure. So already removing the need for water as a moderator is a major plus. Thorium reactors can operate at a thermal efficiency in converting heat to electricity at 45%. While uranium is at an efficiency of 32 to 36%. This is because a temperature increase in the steam leads to more efficient energy transfer, which is due to the thermodynamic properties that are outside the scope of this video. In short, the thermal efficiency is a pro. The radioactive liquid stores the energy of each fission, which is then used to heat up water and then spin a turbine. As we'll soon see, another key convenience with using a liquid substance is that it's very easy to remove waste products compared to the solid bars of uranium. What's most fascinating about such liquid designs is the emergency valve, with a low melting point which allows the emergency freezing plug to melt if the core overheats. Not only that, but the liquid salt reactors do not rely on the use of highly pressurized pipes with steam water, which is why a classic reactor would explode and shoot radioactive waste everywhere if the pumps were to fail. This will not occur for thorium reactors as the salt remains a liquid, and if it does reach the atmosphere, it'll actually turn into a solid. This technology is actually more compact than the uranium design, allowing the technology to be widespread. This is because the containment facility required to maintain the high pressured steam is not required here. So the widespread use of such technology will undoubtedly reduce the CO2 emissions. However, it does come at the potential risk and problem of the weaponization of the U-233. And even if regulated, this is likely to become a large hurdle in making this technology commercially available for everyone. Hence, much of the problems with this design has less to do with the actual engineering and more to do with the implementation and the economics. For instance, an engineering problems with thorium reactors back when they were developed was the salt's corrosive properties. This resulted in the tubes shutting down and the American testing plant closing in 1969 after running for 4 years. However, solutions have caught up, for example, producing thicker tubes to having different corrosive materials of the salt. To better understand why this technology is not mainstream today, we need to go back to the dawn of the nuclear age. This technology was thought back in the 1950s and was supposed to exist then to bring us large-scale portability of energy, such as thorium-powered planes. First was the lack of funding and expertise, as the only experts with thorium power were in the Oak Ridge National Laboratory. It was in 1973 when the US completely discontinued thorium research, and instead funded uranium research, as it was thought to be more efficient back then, likely also hiding the fact that uranium could much easier be used to make nuclear weapons, compared to thorium where such weaponization is not that easy. There were also many problems back then that have now been solved, such as the advancements in material science and semiconductors. In conclusion, uranium was unfortunately chosen. And as we'll soon see, the choosing of uranium over thorium makes thorium much difficult to implement just because it doesn't have the same economies of scale as uranium has. So many viewers might be thinking right now that thorium is a rare element. However, you are actually pretty wrong. The abundance of thorium is actually incredible, 4 times greater than that of uranium, which would satisfy our energy needs right now for over hundreds of thousands of years if used properly. When mining, it is discarded as waste, with 3,200 tons of it being sent back to the desert. Okay, so here is where one of today's business/economic opportunities lie. So China has built an experimental thorium reactor and will begin its operation this month, producing a tiny 2 megawatts of power. So to understand more what megawatts are and gain a better perspective and how to contextualize it with other sources of energy production, you can watch the soon-to-be released video in the card somewhere above. If tests succeed this month of September 2021, China will build a 373 megawatt reactor by 2030. Since the reactor does not need water as a moderator to function, the plant is located on the edge of the Gobi Desert. For a comparison, the moderator in traditional designs is the hydrogen and water, which is good at absorbing the momentum of the neutrons and thus slowing them down to thermal neutron. The reactor's location is already a key advantage, as it creates more certainty for all stakeholders that in the case that if something does go wrong, no civilizations or civilians will be affected. More importantly, however, is that this technology is going to put China in a very powerful position if it does succeed. As the government has stated, it is interested in looking to export this technology. And seeing how nuclear is currently the form of the most reliable green energy production, it comes to no surprise to see other countries attempt to implement this technology to reach their goals. And in that scenario, they're either going to have to innovate the technology by themselves or outsource it to a country like China. The countries that have looked so far into this are Germany, UK, US, and India. And India is worth noting as it has the most thorium resources, about 846,000 tons, 13.3% of the world total, and a weight of 3,109,000 adult grizzly bears. However, the extraction technology in India is more expensive than the extraction of uranium. So creating a more efficient extraction process for India or for any other countries is likely going to be another lucrative engineering opportunity. So before we jump into the costs, you need to understand that much of the backlash experienced by firms is from government regulations and the public perspective on nuclear power being harmful for humans, which is very unfortunate and has stalled innovation in a technology that could have very well brought us nuclear powered planes. However, on the flip side, one could argue that it has prevented nuclear war. One of the best things we can do is to actually change the negative connotations surrounding nuclear energy. I would argue a complete rebranding, such as a change in the name, the building, and the color. Calling art majors, I believe that you can think of something innovative and creative that can change the identity to user-friendly. Largely, the biggest misconceptions that we need to remove is that number one, more people die of any other energy source than from nuclear. And that number two, there are about 100 times more traces of radioactivity emitted from coal plants than emitted from nuclear plants, largely because of safe shielding. However, the economic implications of building such plants are being realized by governments, with an increasing large incentive for government to build plants, largely because the government sees the potential of the excellent circulation of money that it could happen in the economy compared to other commercial plants. So now looking at the costs, nuclear fuel is actually cheaper than coal and natural gas, largely because it is 3 million times more energy dense than coal, requiring around 15,000 times less mass, with thorium being an even cheaper alternative if the economies of scale are appreciated, with the thorium power producing a cost of 1.7 cents per kilowatt hours, with the salt making up 83% of the fuel costs and thorium the remaining 17%. And here's where the caveat comes in. While the fuel might be cheaper, the nuclear plants are more expensive and take longer to build, around 10 years compared to coal and natural gas's 2 years. Hence, it takes much longer to recoup the investment after borrowing, despite the fuel being cheaper. Therefore, while the potential gain is larger and the costs of operating are lower, it becomes less enticing for investors to deal with that level of long-term risk. Essentially, we need to create processes that make the construction of these thorium plants much quicker and cheaper. Thankfully, companies and countries are looking into more innovative solutions to solve this problem, such as Thorcom, which is creating thorium and uranium reactors on container ships. Since its capital and fuel costs are cheaper than coal, and the time of construction being roughly 1 to 2 years, small, replicable technology like this that can be mass-produced is key to large-scale distribution of nuclear power, which is an opportunity just waiting to happen. Other related technologies include small off-the-grid reactors, such as startup Oklo, that utilize spent nuclear power to operate. This is yet another massive opportunity, as off-the-grid manufacturing processes are very difficult to decarbonize, as renewables cannot guarantee to produce a consistent energy source to meet manufacturing demand. As of right now, either micro hydro dams are used or emission-heavy diesel power generators. Hence, small nuclear power plants like these can be used to provide power to manufacturing plants and coal mining facilities and reduce the amount of CO2 produced. There's absolutely no doubt that nuclear energy will be essential in dealing with the climate crisis. Well, as of 2020, the total energy taken from nuclear is about 10%, with the remaining total energy production being shared with coal and natural gas at 36% and 23% respectively. The United States shared 20% of the energy from nuclear, with France taking a whopping 70% from nuclear. This technology will be key for our future energy production, as it's the most reliable source of green energy. In fact, an MIT study looked at 1,000 different scenarios for getting to zero emissions in the US. And all of these involve the heavy use of nuclear power for sustainable energy production. So how about the impact of storing radioactive nuclear waste? As of September 2021, there is virtually no place to store nuclear waste for the long term, with the exception of the Onkalo plant in Finland. This site is building a series of tunnels half a kilometer underground in bedrock. This $1 billion project started its construction in 2005 and is scheduled to complete in 2031. Its funding has been the contribution of two major energy players in the industry, using the cut from their electricity profits to build this site. Other methods, such as dry casting, work for the short term. However, there is no guarantee that these structures will remain where they are for upwards of tens of thousands of years. However, long-term waste strategies might actually not be necessary. In fact, thorium reactors might be our best bet at mitigating the negative impact from such harmful elements, which are known as Transuranic elements. In fact, the probability of the thorium reactors producing its most likely transuranic is Neptunium-237, which is less than 2%, which is 20 times less likely than the probability of the standard reactor producing transuranics such as plutonium, americanium, etc. What's even better is that the small amounts of transuranics allow for them to be recycled, as they can also be fissioned. This is also where the liquid salt presents a very clear advantage, as the fuel being in liquid form allows for the entire recycling process to be easily filtered and reprocessed compared to the solid of the standard core. What we need to understand is that this waste is both a liquid and a gas, which means that it can be separated relatively easily. And because of that, the different half-lives can be stored in different areas left to decay. Taking this recycling into account, one produces 1,000 times less transuranics. Hence, the radioactive culprits here are lighter elements, such as cesium-137 and strontium-90, that have a half-life of 30 and 29 years. These half-lives are, well, much shorter and much better than the hundreds of thousands for transuranics. Final economic and sustainability opportunity lies in the fact of using nuclear power for more than just electricity. More specifically, we can use nuclear power as a source of heat for other processes and sectors. For instance, consider processes such as the Haber process, or thermally driven water desalination, or really the manufacturing of metals that are required to be heated up, a smelting process, or even nuclear power planes which heat up air by fission rather than gasoline. So instead of using coal/gas options to generate heat to create these processes, this thorium technology can be applied to all of these industries to provide reliable thermal energy. In many processes that rely on electricity to create heat, with this implementation, you are also increasing energy transfer efficiency as you remove the need to convert electricity energy into thermal. And if you compare these thorium reactors to traditional light water reactors, you'll see that they produce more heat at 700 degrees Celsius compared to the 300 degrees, and are also more practical to use due to their not reliance on high pressure and protection storage facilities that light water reactors need. This is actually a massive opportunity with the ability to transform the world's emissions by shaving off emissions in all sectors, but especially in the industry and commercial sector, which one can see directly impacts 53% of the residential emissions. And since the world is already incentivized to reduce greenhouse emissions in the next few decades, it's very difficult to see this type of heating technology not being implemented, especially with all the government grants in green technology, are the startups that can provide this technology in a safe manner to communities. As implementing thorium reactors as a consumer product the same way one buys a gasoline reactor is unlikely to happen anytime soon. In conclusion, thorium power is still in its earliest stages. And I like to ask myself all the time where our civilization would have been if we would have developed thorium rather than uranium back in the 60s. And what I find most interesting about this all is the various opportunities that lie within sectors of the economy that are so often hidden from our everyday life, such as technology, material manufacturing, and heating. From this, I'm excited to see this technology reach scale in the coming decades and the resulting impact on electricity power, and heat production across all industries. This goes without saying that if you found this video informative, please do me a massive favor and share this with 3 other friends that you know can benefit and learn something from this information. Videos like these take dozens upon dozens of hours to make. And while I do like making these videos, I would very much appreciate any support that you can give me. That is it for this video. Thank you very much for watching. And until next time, keep innovating. I'll see you in the next video. Goodbye.